Hello, my name is Jun Zhang from Nanyang Technological University, Singapore. I'm going to introduce our work on 4DRadarSLAM, a 4D imaging radar SLAM system for large-scale environments based on post-graph optimization. This work is co-authored with Huayang Zhuge. Firstly, a brief introduction. The motivation is that the visual and the LiDAR SLAM may fail in adverse weathers such as rain, snow, smoke, and fog. So the objective of this work is to propose a 4D radar SLAM system for all weather perception. A 4D radar is shown here. It can provide X, Y, Z, and velocity information. The key contributions is that we presented a full 4D radar SLAM system. In the front end, the scan-to-scan matching based on GICP, and we introduced the uncertainty of each point. In the loop closure module, we introduced the intensity scan context and the odometry check module. In the back end, we use the post-graph optimization with the GPS optional to get the optimized global trajectory. We also open source our code on GitHub. A video is shown here that the SLAM can work robustly in the smoke environments. Here the smoke comes again, and it does not affect the radar. The methodology mainly consists of three parts: the front end, the loop detection, and the back end. Next, I will introduce each module one by one. Firstly, in the front end, we will pre-process the point cloud. That's to say, to estimate the ego velocity of this radar. Then, with this velocity, we can obtain the absolute velocity of each point. Thus, we can remove the dynamic objects so that we can only keep the static points for the next processing. In the odometry calculation, it is based on the GICP as shown in this loss function. But we considered the uncertainty of each point as shown here in this CP, the covariance of point. CP is the covariance of each point. In the loop detection module, we introduced 4 rule-based steps to filter out the unlikely loops. For example, a new loop should not be too close to the previous loop, and the loop should be within a certain radius, and the query frame and the retrieved frame should have similar altitude. For example, 2 meters, and the query frame and the retrieved frame should have a similar U angle. That's to say 20 degrees. So the loop pre-filtering will avoid too close loops and will get the spatially close 2 frames. And the 2 frames should also be attitude similar. To find out the loop closure, we use the intensity scan context. This one picture shows the process to get the scan context image of 1 point cloud. Each bin, we will choose the highest intensity of as the pixel value in this scan context image. Then the query image here shows an example of the query image and the retrieved frame. In the odometry check, the basic idea is that when the robot travels from T0 to the T8, then there is a loop closure. Then the trajectory, the odometry from T0, T1, T2 to T8 should be close to the transformation obtained from these 2 frames, the TLC. This is the basic idea of this odometry check. In the back end, we construct the post graph and solve it with the G2O. And GPS signal can be integrated as a constraint if it's available. For the experiment, we tested the algorithm with 2 platforms, a handcart and a car. The velocity is different. And with 5 data sets, a car park, in garden, and in the campus, 1 kilometers, and 2 loops in the campus, about 4 kilometers. Next, we will introduce the experiments with these 2 data sets, the garden and the loop 1. Firstly, we use a hand cart. It's move about 1 meters per second in the Yunnan garden. It's a garden environment, so it's an unstructured environment. The total length is about 339 meters. Here shows the result. Here shows the GICP. Here shows our proposed APD GICP. And here shows the GICP plus the loop closure. And here shows the APD GICP plus the loop closure. We can see in the middle the image of the garden. So this is an unstructured environment because it's full of trees and grass. When the loop returns, the loop closure will be detected and triggered. Then the global trajectory will be optimized. This shows the top-down view of this garden environment. The red point shows the current point cloud, and the colored point cloud is the mapped point cloud. And the total length is 339 meters. A loop is triggered, and the post graph will be optimized. In the second scenario, we use the car platform. It moves around 30 kilometers per hour in the NTU campus. The total length is about 4.8 kilometers. Here shows the video. This is the camera image from the camera. This is the GICP. This is the APDJ plus the GPS. This is the GICP plus loop closure. When the robot returns to the starting point, we can say the loop closure is triggered, and if the GPS is available, the trajectory is already overlapped. But without loop closure and GPS, the trajectory is drifted a lot, as shown here. So to conclude, in this work, we proposed a 4D EBG radar SLAM for adverse weathers. In the front end, our proposed APD GICP is better than GICP for small-scale datasets. Second, once a correct loop closure is triggered, the accuracy can be improved significantly. Thirdly, if GPS signal is available, it will also improve the performance by a large margin. In the future, we will integrate the IMU to achieve a more robust performance. And thank you for your listening.